Hi, everyone. This talk is about computational problems, what we call oracle problems, that can be solved with polynomial depth quantum computation, but as we'll see, cannot be solved with computational resources that only have limited quantum depth, low quantum depth, even when interleaved with classical computing. All right, I'm Matt Kudron, and this is joint work with Sanketh Minda. So I think the quickest way to introduce this topic is by stating two conjectures that were part of what inspired us to work on the topic in the first place. So these conjectures are about interleaving quantum computation, low-depth quantum computation, and regular polynomial depth classical computation. So the first one is a conjecture of Richard Jozsa, and it says that any polynomial time quantum algorithm can be implemented with only log-n or order of log-n quantum layers interspersed, so he means layers of quantum gates, interspersed with polynomial time classical computation. This is a very interesting statement because I think it's intuitive to most people that in general computations, many computational problems may require polynomially high depth. The computation may have to be high depth, but Jozsa is talking about something a little bit more subtle than that. He's asking, isn't it perhaps possible that in quantum computations, the high depth part of the computation can always be outsourced to classical pre or post processing, leaving only a low depth actual quantum part of the computation? So that's the question, and we'll discuss a little bit more about that later. And there's another conjecture that came out right about the same time. These dates are just the dates I could find to cite these conjectures. It's not clear which one is first, but so there's a conjecture due to Scott Aronson that says there exists an oracle, and I'll say a bit more about what an oracle is later, or what an oracle problem is later on in the talk. But it says there exists an oracle which separates BQP, so polynomial time quantum computations, from BPP to the BQNC, which is a model that I'll define in the next slide. It's essentially a model for interleaved quantum, low depth quantum computation and regular polynomial depth classical computation. So Aronson is suggesting that there is an oracle problem that can be solved by polynomial time quantum computation, or polynomial number of quantum queries, cannot be solved, and yet cannot be solved by this more limited class of interleaved quantum and classical, low-depth quantum computation and classical computation. So let me say now a bit more about that computational model, because it is the one that we'll be focusing on for the rest of this talk. So this is what that model looks like, BPP to the BQNC. Or actually, for technical reasons, we will refer to this model as HQC, hybrid quantum computation. It is, for the purposes of this talk, it is the same thing as BPP to the BQNC. The difference is technical, and I won't get into that. It contains BPP to the BQNC, and they're morally equivalent, at least for our purposes. Okay, but this is the class of computations which can be performed by circuits which have the form shown here. They are interleaved quantum classical circuits. So the blocks labeled Q are quantum circuits of low depth. So in this case of logarithmic or polylogarithmic depth. And the blocks labeled C are classical circuits of polynomial size and depth. Okay. And the computation in these diagrams proceeds from left to right. So X is a bit string input, and then there are padding, like extra wires padded with zeros for side computation. And on the far right would be the output after polynomially many interleaved layers of low depth quantum and regular polynomial size classical circuits. And essentially the only real rule restricting these computations is that after each low depth quantum layer, you have to measure all of the qubits, you know, that quantum layer or quantum tier. We will actually call these blocks tiers, quantum tiers, classical tiers. After each quantum tier, you have to measure whatever quantum state is being produced in the computational basis, which reduces it back to a bit string. And then you use that bit string as the input to the next classical tier. The output of that classical tier is the input to the next quantum tier, and so on. Okay, so that's how this model works. And then at the end of the computation, there would be one special bit, which is the decision bit. Okay, so HQC is the class of languages which can be decided by uniform algorithms using circuits of this type, uniformly generated circuits of this type. Okay. So that is HQC, and in this work we will actually resolve this conjecture of Aronson. So we will show, that's our main result in a sense, is showing that there is an oracle which can be performed, the oracle problem that can be solved in BQP but cannot be solved in this model, HQC. All right. So let me now say briefly, so this is the model we'll use throughout this talk. It turns out Joza in his conjecture was actually referring to a different model. It turns out there's a different way that you could interleave quantum and classical computation, which is not clearly comparable. And our oracle separation will apply to this model as well, but I won't talk about it in detail just due to time constraints. Okay, so now I want to just say, having defined the computational model, I want to say just a few quick things about what makes this problem interesting and why it wasn't resolved immediately, I guess. So first of all, in order to provide an oracle separation between BQP and HQC, it is necessary to, as prerequisite, that oracle problem must separate BQP and P, classical polynomial time. And the reason for that is that HQC trivially contains P. So any polynomial time classical computation can be done in HQC. Okay, and you know, so that's a simple observation. What's the point? The point is, if you look at the most famous and well-known oracle separations between BQP and P, while they are problems that can be solved in a polynomial number of quantum queries but cannot be solved with a polynomial number of classical queries, they also all seem to have the property that they can be solved in constant quantum depth, meaning the number of queries and also the depth of the queries you need to perform, so the number of adaptive queries you need to perform, and indeed just all the quantum gates you need, all add up to only a constant depth, and the rest of the problem can be done with classical pre- and post-processing. So in other words, these are not candidates for separating BQP and HQC because they can be solved in BQP, but they can also be solved in HQC. All right, that's true for all of these shown here on this chart, except for one, which is called the welded tree problem. And that's a little bit of foreshadowing for later in the talk. All right, so that's one interesting thing, is that many of the known oracle separations would not work off the shelf to solve this problem. Separately, another interesting observation is that HQC contains some really interesting algorithms. In particular, even the quantum factoring algorithm, one of the most famous known quantum algorithms to factor integers in polynomial time, that can actually be implemented in HQC. So it turns out that that can be implemented with log depth quantum circuits and polynomial classical pre- and post-processing. So this is a result due to Cleve and Watrous. So that means that we don't expect HQC to be contained in classical polynomial time, unless you can factor in classical polynomial time. And it also suggests that maybe there's not a super simple characterization of HQC. Yeah, maybe some work is required. All right. So without further ado, those were some points about why this is maybe interesting. And without further ado, I'll state the main result of our work, which is that the welded tree problem, which is what I alluded to on the past slide, and then I'll concretely define it shortly. The welded tree oracle problem cannot be solved in HQC. So this is our main result. And it was previously known that the welded tree oracle problem, actually in the paper about 20 years ago that defined the problem, it was shown that this problem can be solved in BQP. And so these two facts together prove the Aronson's conjecture about this oracle separation. So they provide an oracle separation between BQP and HQC, and perhaps suggest a counterpoint to Joseph's conjecture, albeit only relative to an oracle, whereas Joseph's conjecture was unconditional. Okay, so this is a good time to point out that there is actually an independent and concurrent work in this conference, in Stock 2020, that also proves this an oracle separation, although they actually, interestingly, they use a quite different oracle. And this is in a paper on the need for large quantum depth by Naihui Chia, Kaimin Cheng, and Qingyi Lai. So if you want to see their approach, that's also available in Stock. Okay, for us, the pertinent thing to do now is to define the welded tree problem, this welded tree oracle problem. So we can talk a little bit in the time we have left just about a kind of a flyover tour of how to prove this result. Okay, so the welded tree oracle problem has to do with a graph. The graph or graphs of the type that is depicted here. This graph consists of two binary trees, one on the left, one on the right, joined together at the leaves in the middle by a random cycle of edges. This is why it's called the welded tree problem. It's like they're welded together by this cycle. Okay. In this problem, the vertices have labels, and there are two special vertices that have names. So the roots of the two trees have names. The root of the tree on the left is called the entrance, like an entrance to a maze, and the root of the tree on the right is called the exit. And also, in addition to that, every vertex in the whole graph has a distinct or a unique random bit string label of length 2n, so 2n bits long. All right. As I mentioned before, we actually, in the welded tree problem, we will only have access to this graph via an oracle. So the only information we have about this graph will come from this black box function, which implements this oracle for this particular graph. This is why it's called an oracle problem, and you'll see a little bit more how that works later if you're not familiar with oracle problems. So this black box function, k sub t, the way it works is that if you input the label of a vertex in the graph and a color just specifies an edge emanating from that vertex. And I won't get into how the edges are colored. It's fairly straightforward, but I won't cover it just due to time. So you basically give the oracle a vertex label and the color of an edge, and it tells you the label of the neighbor of that vertex along that edge. And it does that unless the information you've given it doesn't make sense. Like if you give it a bit string label that does not correspond to any vertex in the entire graph, because there are many more 2n bit strings than there are vertices in this graph. Then it will just return invalid, which we're going to call the all one string. So it just spits out, well, that's invalid. Okay. And because we're discussing quantum algorithms, the quantum part of HQC, this computational model, will be allowed to query this oracle in superposition. All right, So in other words, it can provide a quantum superposition of bit strings at which it wants to query the oracle, and the oracle will return a corresponding superposition over the answers. All right, so the way that the welded tree problem works is that the input to the problem is a black box for a given graph. So all you know about the graph is this black box, and you're also given the label of the entrance vertex. And that's it. And in order to solve the problem, you have to find the label of the exit vertex for the graph. So you have to somehow, you can query this black box at the label to the entrance vertex and learn the neighbors of the entrance. And maybe you can walk around, do some kind of walk inside this graph, but you have to find the label of the exit vertex at the end of the day. Okay, what is known about this problem, or what was previously known? A lot of it came from this paper in which the problem originated, this paper of Childs, Cleve, Dioto, Farhi, Gutman, and Spielman, Childs et al. And so first thing is that they showed that this problem can be solved in BQP, so with a polynomial number of quantum queries and also quantum computation. And their algorithm works by a technique called a quantum walk, which I won't get into in detail, but I guess the main point to take away is that in this graph, there are an exponential number of vertices. These are binary trees of height n, so they're on the order of 2 to the n vertices. And yet somehow you can solve this problem with just a polynomial number of quantum queries and quantum computation. So that's what makes this interesting. And in addition to that, they proved a lower bound. They showed that you cannot solve this problem with a polynomial number of classical queries. All right, at least not only with exponentially small probability can you do this. All right, and in a sense, our main result can be seen as like an upgraded version of their classical lower bound. We show that not only can you not solve this problem with high probability, with a polynomial number of classical queries to this oracle, you actually can't even solve it in this computational model where you have a polynomial number of classical queries interleaved with log depth layers of quantum computation that are allowed to make quantum queries. So it's allowed to use this oracle as a quantum gate that you can query in superposition, but only logarithmically many times adaptively before you measure. So this model HQC. All right. So let me say now, in the time that I have left, just a little bit about how this proof works. So first of all, the like flyover description of this proof is that it works. You can think of it as a proof by contradiction. So we assume towards contradiction that you could solve this problem in HQC. So there is an HQC algorithm with access to this oracle that finds the label of the exit vertex. And then we come up with a classical query algorithm which faithfully simulates this HQC algorithm and therefore produces the valid label of the exit vertex as well. And it does so with only sub-exponentially many classical queries. And it turns out that that is a contradiction of one of the results in this earlier paper, the Childs et al. Paper. And it turns out that they show that it's impossible to produce the valid label of the exit vertex with high probability, even with sub-exponentially many classical queries. So then we get our contradiction. Okay, so that's the high level of the proof. How specifically does our simulation algorithm work? Because now the rest of the proof is really just about simulating this HQC query algorithm with a classical query algorithm. Okay. So first of all, because we're now just working at the level of query algorithms, we only have to be careful about the number of classical queries we make. We can use arbitrary classical side computation, all right? And so we can keep track of the entire quantum state at any given layer throughout, starting at the beginning of the HQC computation and walking through layer by layer. we can keep track of the entire state, write out the whole thing, all the amplitudes and everything, except whenever the HQC algorithm made a quantum query in superposition, we now have to update our description of the state correspondingly, but we only get to use classical queries to do that. So the main hurdle that we have to deal with is, how do we update a state in a manner corresponding to this quantum query, but when the query was in superposition? So like this quantum algorithm, for example, can query the oracle at a superposition over every possible 2n-bit string. Yeah, and so how do we find the state produced by that query without having to ourselves make classical queries at all of those 2n-bit strings, which would, we only want to make a sub-exponential number of queries, not an exponential number. Okay, so just very briefly, the way that this can be done is you first keep track of all of the vertex labels ever returned up to a given point in your classical query simulation algorithm. So up to a given point, you've only queried certain labels, and only certain labels have been returned by those queries. And it turns out to be a fact that you can prove, and I won't say how, that the state that you're keeping track of up to that point, the amount of mass of amplitudes that it has on valid vertex labels that have not yet been returned by any of your classical queries can only be exponentially small. So it turns out you can prove this. And it's relatively straightforward from the Childs et al. Paper to prove this. And so that means that what you can do is, when you're given this giant superposition and you're supposed to implement a quantum, this quantum oracle action on this giant superposition, you can go through that superposition over queries and say, well, any query I've seen before, I'll do an actual classical oracle call to find out the answer to that query. Any bit string I've seen before, returned by the oracle in the past. But any bit string that I've never seen before has never been returned by the oracle in the past, so it's not in the set V. I know that there's only an exponentially small chance that that is a valid vertex, so I'm just going to guess that it's invalid every time, right? So it turns out you can do this, and you induce some error. Sometimes you're wrong, but you only induce exponentially small error. And this technique gives us an algorithm which allows us to simulate a classical query algorithm which can simulate HQC query algorithms, but only for a constant number of tiers of HQC, or even a square root n number of tiers of HQC, but not a full polynomial number of tiers. What happens is, if you try to do this simulation for a full polynomial number of tiers, that set V of bit string labels that we're keeping track of, that vertex labels that have been returned by the oracle in the previous part of our algorithm, that ultimately grows larger than sub-exponential, in which case the bound we're using to arrive at a contradiction becomes trivialized. So if we want to simulate, if we want to get this result for the full class HQC, we actually have to do much better than this. So how can we do better? The idea is we want to preserve the key property we were using earlier, which is this property that only, at any given point, if we're keeping track of all the vertices our classical queries to the oracle have ever unveiled, the amount of mass that the quantum state can have on valid but unknown vertices has to be exponentially small. We want to keep that property, and yet we want to reduce the number of vertices that we are remembering, that we're keeping track of. Okay, so that's the goal. I'll just give you the intuition for how this is accomplished. That's all we have time for. The intuition is that there is one property left of HQC that we haven't leveraged. And that property is that between the tiers in an HQC computation, all the information that is passed is in a polynomial-sized bit string, passed from one tier to the next. The output of one tier that becomes the input of the next tier. And so intuitively, you shouldn't have to keep track of an exponential amount of information, an exponential number of previously queried vertices, in order to know the information that is passed from one tier to the next, which in a sense should be all the information you need to simulate the algorithm going forward. Okay, so the idea is we should be able to prune the set of vertices that we are remembering as we step from one part of the algorithm to the next. But the big question technically, the technical hurdle, is how do we do this? And the answer in words, which is not very mathematical, but the answer is that we can forget the vertices which have the property that they could not have been guessed with high probability. So those vertex labels, we can safely forget those vertices whose labels could not have been guessed with high probability by an observer who knows the bit string passed between the two tiers, between the cutoff between tiers that we're currently focusing on, and also knows all the vertex labels we want to remember as we pass from that tier to the next. And okay, so this is a little bit technical, and it's probably not possible to completely convey it in the time constraint. It's also a little, there is a circular aspect to this definition, because the vertices vertex labels you're allowed to safely forget depend on those that you want to remember. So there is this circular property. But it turns out that there is a way to prune down the vertices and maintain the property that you need in this algorithm. And it is accomplished by a rather involved, greedy algorithm. So this is way too much information overload. I haven't defined anything that's on the screen here. But the point is, there's just a somewhat involved, greedy algorithm. And the way that it works is by, we basically set up a greedy algorithm such that we know that the vertices we remember have the correct property if this greedy algorithm terminates, this pruning algorithm terminates in a polynomial number of steps. And the rest of the proof comes down to showing that that algorithm terminates, which you can do with a sort of complicated counting argument. All right, and that